Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be looking at Chapter 10 on power and sample size. So I'm hoping by the end of this chapter, you'll learn how to assess the power of a statistical test and also to determine the required sample size for a study. And this will help you achieve the learning objectives of distinguishing between statistical significance versus relevance, scientific relevance, identifying and explaining statistical methods, assumptions, and limitations, and making evidence-based decisions. So, power analysis. What is the meaning of statistical power? It's the probability of detecting the interesting feature in the data when it actually exists. That is, when an effect is there, we observe it. And the probability we give that is 1 minus beta, where beta is the probability of a type 2 error. We've been working with alpha all semester, which is the probability of type 1, and we don't really think very often about the probability of a type 2 error, but when you make a type 2 error, you don't find the interesting effect. And so 1 minus the probability of making that type 2 error is the probability of finding the interesting effect when it's there. And we often want this power to be as high as possible. So let's take a look at an example. Let's say that we have a simple study with drug A and a placebo group, and that the drug truly is effective. So the power is the probability of finding a difference between the two groups. Basically, you're finding that the drug was effective. So imagine we have a power of 0.8. That is, for clinical trial reasons and for a lot of study reasons, when you're proposing a study to the National Institutes of Health or National Science Foundation, they'll often request that you have a power of at least 80%. And so imagine that we had a power of 0.8 and that this simple study was to be conducted many times. Right? In practice, you would only conduct a study once, but say we would, in this hypothetical example, we're going to conduct the study many times. So having the power of 0.8 means that 80% of the time we would actually find a statistically significant result. And it also means that 20% of the time we'll have a type 2 error, and that we don't observe the interesting difference. Okay. So let's take a look at a figure that this code creates right here. And this will illustrate what all the names and definitions of things that are important to consider. So let's let mu naught be the mean for one sample test under the null hypothesis, and we'll let the gray diagonal lined distribution be the null distribution under the null hypothesis. Okay, so it's centered at mean mu naught, and it has a certain standard deviation, which is determined by the population mean. The population standard deviation and the sample size. And given this null hypothesis, let's say that we have an alternative hypothesis of that the true mean is greater than the null hypothesis. So that means our right tail is going to be the rejection region, and it's the right tail that we'll also calculate the p-value under. And so the critical value is the value beyond which the p-value is less than 0.05. Okay, so this right gray tail is 5%. Now, we also have an alternative hypothesis distribution, which we don't often think about because we don't have a specific alternative. but in order to calculate power, we need a specific alternative. So let's say that the true value for the mean is mu1. Okay, it's some number of units greater than mu naught, and it's centered here. So this allows us to now calculate type 2 error, because it's under the alternative hypothesis that you calculate the type 2 error and the power. So if that is the actual distribution, or rather, the actual distribution of the statistic, and it's not under the null, then if you were to, say, sample many times from the population and calculate the statistic, it would actually follow this red and green curve. All right, and that means most of the time, notice we're in the rejection region. That's in the green area, and that's the power. That's the probability of observing the interesting effect when it's there, and it's there in this case. And type 2 error is the unlucky situation where you observe a test statistic that's consistent with the null distribution in this red region, but in fact that was a statistic that was drawn from this red and green curve. So it had a high power or high probability of being detected, but we got unlucky and we got the sample off in the left tail, and we failed to reject the null hypothesis, concluding nothing interesting is happening. So those are the areas associated with, first of all, we got the curve associated with the null distribution. We have the rejection region, which is to the right of the dashed line, which is a critical value. And under a specific alternative hypothesis, the area in the rejection region is, under the alternative curve, is the power, the green part, and the red part is the probability of type 2 error, which is called beta. Beta is the red area. All right, so if I scroll back up to this paragraph, the one sample power figure, those are the features that this paragraph is describing. All right, so let's take a look at an example. So imagine we could manufacture a drug that would enhance your IQ. Okay, so we might think of caffeine as doing this on a temporary basis. Okay, says someone who doesn't drink coffee. So say we have a random sample of 25 people, and we know that the distribution of people for IQs are normally distributed with a mean of 100 and a standard deviation of 15. So we're truly drawing a random sample from the population of people. So we're going to administer the drug, wait for a little while for it to take effect, and then test our subject's IQ and ask whether their IQ is higher than the null value of 100. So assume that we're so confident in our belief that the drug would either increase or have no effect that we can entertain a one-sided directional hypothesis. So the null hypothesis is that mu is equal to 100, and the alternative is that mu is greater than 100. All right. So it's possible, okay, in this hypothetical example, that the drug is going to increase our IQ, everyone's IQ on average, by 15 points, an entire standard deviation. That would be sort of miraculous, right? And, okay, so when we're doing a power calculation, we would like to specify an exact alternative hypothesis. And 115 in this case seems a bit outlandish. And so what we really want to do is determine a minimal non-trivial effect size. So what is the smallest increase that we would consider to be non-trivial? So say that if you increased your IQ by 2 points, that would be an interesting effect. It would be a meaningful increase. So let's compute our power under this situation. So we know the mean under the null hypothesis is 100. we know the mean under the alternative hypothesis, which is 102. We have the standard error of the mean, which is the 15, which was the standard deviation of the population, divided by the square root of the sample size, which is 5, and that ratio gives us 3. So if I scroll back up for a moment to this image, our null hypothesis on the left is centered at 100, the alternative centered at 102, and both of these normal distributions have a standard error of 3 units. So the standard deviation of each of these curves is 3. And then we want to calculate what's the area under what's the green area equal to. In fact, you could modify the code that creates these plots to create this exact example by determining what the mean and standard deviation is under both the null and the alternative hypothesis. So you're welcome to play with some of the parameters in the code to look at this example. All right, so the green area, okay, so this is what this says here. Calculate, calculate, calculate. Okay, and what we end up, let's see, I guess we need to walk through this a little bit. So the green area of the upper tail curve is, of the gray hatched area is alpha, so we're going to let that equal 0.05. And so then how large a sample mean need to be for us to reject the null? Okay, so basically we need to determine the critical value. So if I scroll back up for a moment, we need to know what this critical value is. So mu naught is 100, mu 1 is 102. So what is our critical value? Well, it's 1.645 standard deviations above the mean. The standard deviation is 3. I'm going to page back down. And so here we are, 1.645. That gives a right tail area of 0.05. Multiplying that by 3, which is the standard deviation, adding 100 to that, and so it needs to be as high as basically 105 is our critical value. So any test statistic that we observe that's greater than this, we will reject the null hypothesis. So now, under the alternative hypothesis, what's the probability of observing something greater than 105? So that is the power of the test. So if we compute the probability of that, okay, I'm going to skip on down, it's about 16%. So in this case, if I scroll up for a moment, these two curves are not very separated in the case we're describing. They actually overlap quite a bit. And so we end up with a green area that is quite small, about 16%. Basically, imagine shifting this green curve to the left of the critical value, so the two peaks are close to each other. So that means the right tail of the green curve is pretty small. Okay, I'll page back down. So what happened? So that was a case where 2 units, an IQ increase of 2, we were calculating the p-value or the power for that. What happens if in fact 5 was the amount? Then what's the power? So we perform this same calculation and we get about 50% power if it was 5 units of IQ increase. And okay, I shouldn't teach that way. It's easier to detect large effect sizes than small effect sizes, and that's what this is demonstrating. All right, so let's suppose we conduct a two-tailed test, since the drug could actually decrease your IQ. So then you've got to split alpha into both an upper tail and a lower tail and make this calculation. So I'm going to sort of skip over this, but I recommend that you read on through. And what the main conclusion is that if you can correctly predict the direction of the effect, a one-tailed test is going to be much more powerful than a two-tailed test because you are guessing at the correct tail area, and you're going to have a larger rejection region in the direction that where the alternative distribution actually lives. All right. So there's different ways of looking at this problem, and these paragraphs describe those different ways. One is that there's lots of variables in play. There's the effect size, so how far, let me scroll up for a moment. So there's the effect size, that basically like the difference between the null hypothesized value and the value under the alternative hypothesis. There's the standard deviation of the population. There's the standard error of these curves. There's the alpha level. And once you know those four things, you can calculate power. So there's basically an equation that has 5 variables in it, and you have to know 4 of them in order to calculate the 5th one. So if I page down again, okay, so anything that decreases the standard error will increase power. Oh, did I mention sample size before? Sample size is one of those variables. So if you increase your sample size, your standard error goes down. If your standard deviation of your population decreases, then your power will also increase. Alpha, if alpha decreases, power decreases. So there's all these relationships between the values that go into calculating power. Okay, so let's talk about effect sizes. Effect sizes are often based on standard deviations of the population So let mu naught be the null hypothesized value. Maybe it's 0 for a 0 increase in IQ. Mu1 is going to be the increase in IQ. So this difference is how much we've increased in IQ. Divide that by the standard deviation of the population, and that is our effect size, D. So in the case of the IQ points, we had a null hypothesized value of 100. 105 was the predicted IQ under when you take the drug. The standard deviation of the population was 15, and so we had an effect size of 1/3. This is a fairly small effect size. And Cohen, a statistician, defined conventions for different effect sizes. So here we have small, medium, and large of 0.2, 0.5, and 0.8. So 1/3 is 0.33. It's sort of between small and medium. And these are determined on the percent variance that is being explained for either a 1 or 2 sample test of means. And there's all sorts of other tests that Cohen effect sizes are defined for. These tend to actually, in practice, tend to be a little bit larger than we observe. Small, medium, and large effect sizes, if you were to quantify this under what we observe in many tests, would actually be smaller than what are here. So I tend to think of a medium effect size of 0.5 being fairly liberal, and maybe I want to bring this down to a little bit. Okay. Okay. All right. Let's talk about sample size. So we often do a power calculation in order to determine how many subjects do I need to detect an effect with a certain probability or power. Okay? So there's lots of questions that are related to that you'll need to answer first before you determine your sample size. First of all, how much power do you want? Typically you'll set that as 0.8 or 80%. What is the likely size of the effect that you're trying to detect, or what's the smallest effect that you'll consider of being importance? So that's the effect size. What criterion of statistical significance will I employ? So that's related to, say, the test statistic, whether you're doing a t-test or not. Criterion can also be whether it's a one-sided test or a two-sided test. What's the standard deviation of the population? You typically don't know the standard deviation, but you could estimate it once you draw a sample. And if you've got correlated sample designs, we'll also need the correlation between the groups. And once you have that information, then and the criterion of statistical significance, this will also be, say, alpha equals 0.05 for the type 1 error. Once you have all that information, you can then finally solve for the sample size, which is what we were looking to answer in the first place. Okay. Okay. So we often don't consider type 1 and type 2 errors equally serious, unfortunately. And I would recommend that those type 1 and type 2 error values be determined on the context of the problem. So, for example, imagine you're working on a diagnostic strategy for cancer, and a type 1 error is that someone does not have cancer, but you tell them that they do, right? So there's some cost when you tell someone they have cancer when they actually don't. They go on to take additional tests, which have their own risks. The person may become seriously depressed or scared or have all these negative feelings, and so on, right? So that has some cost, and that should go into your determination of what your type 1 error is. Type 2 is that someone has cancer, but you fail to detect it. And that has danger, because then they live with cancer for a longer period of time before they catch it. Perhaps they have it, perhaps it ends up metastasizing, and they end up dying from it because you didn't detect it early enough. So that has a cost. So you should determine what the actual value of these type 1 and type 2 errors are in the context of your problem, and you should set them in a relative way to take them seriously. Okay? If we wanted to take them equally seriously, then we would set type 1 alpha to be the same as the type 2 error, beta. So that we would be about 5% and 5%. And if that was the case, then it would mean that we would want a sample size to give us 95% power. But 95% power often means that we would need a huge sample size and be much too expensive. So the common convention is to try to get at least 80% power when we have a 5% type 1 error rate, and then calculate the sample size based on that. And there's lots of ways to do this. Okay, you can buy software to do power calculations. There's plenty of books on power calculations. There's interactive web apps. You can download programs off the website. There's a nice book on, or article on power calculations. In the rest of this chapter, I show you how to do this in R for a certain set of problems, and you can also simulate what the statistical power will be under certain tests. Okay. The last things that I want to tell you. So here are some power curves. We'll interpret some power curves, and then I'll give some practical advice about power analysis. Let me zoom in just a little bit. So on the left-hand side, we have three variables plotted together. We have the power on the vertical axis between 0 and 1. We have curves for different sample sizes. So the blue is for a small sample size of 5, and the green is for a large sample size of 100. And then we have the effect size. And these power curves tell us what is the power, that's the probability of rejecting the null when the null is false, when we have different effect sizes at different sample sizes. So you can see when we have a small sample size of 5, even as the effect size gets really large, the power increases very slowly. And in fact, even when we have an effect size of 1, we still only have a power of detecting that effect 60% of the time. Whereas if you have a huge sample size, or let's just stay let's choose an effect size of 0.2. Okay, when we have a sample size of 5, we have a power of, who knows, maybe 0.05. When sample size 10, we go to the red curve, then maybe we have a power of about 0.12. When we have a sample size 25, that gives us maybe a 0.3 probability. And then finally, when we have a sample size 100, we have about an 80% chance. So that's how, for a given effect size, how the sample size affects the power. And we often work backwards. We want a power of something, and we solve for the sample size for a given effect size. The plot on the right plots the same information, basically, but flips the axes. So now we have sample size on the horizontal axis and the effect size as different colors. We have small effect size as blue, a large effect size is green, and so if you wanted to detect a large effect size, you can see that how many samples along the horizontal axis you would need in order to, say, have 80% power. Whereas if you have a smaller effect size, say 0.2, you just need to keep taking samples and more and more and more samples. You know, who knows, it could be as big as 800 samples before you get to 80% power. All right. What are reasons to do a power analysis? And these are reasons that are brought to the Statistical Consulting Clinic almost daily. I've been asked probably over 100 times to do power calculations for biologists and biomedical scientists. And these are some of the reasons that they come to me. Perhaps the most common is to determine the number of subjects needed to detect a given effect size. And many people will want to know the minimum number of subjects because collecting data is expensive, but this is often not a good idea. You want to give yourself some leeway, some margin of error, because there's a lot of guesses that go into a power calculation. You're guessing the effect size, you're guessing the standard deviation of the population, and you could be wrong by big amounts and not know it until you actually collect your data. Additionally, power analysis can be used to determine the power given an effect size and a number of subjects available. So if you know, the best power or the best sample size calculation goes this way: how much money do you have, and divide that by what it costs to collect each observation. Round that down to the nearest integer and buy coffee with the leftover. So if you've got $100 and it costs $2 to collect each observation, your sample size is 50, because that's 100 divided by 2. And given the sample size that you have, what's your statistical power under a certain effect size? Okay, so that's a standard way of doing that. And that will give you a sense of whether you're underpowered. If you only have 10 or 20% of detecting that effect, that says that it's probably not worth doing this experiment. Or maybe you want to measure something different. Okay, you have to make some decisions there. A power analysis is often required as part of a grant proposal. That's where I do that the most. And finally, doing a power analysis is often just part of doing good research. Before you get started, make sure you've thought everything through and that you're on the right path. Okay? There's lots of limitations to doing power analysis. Even though there are advantages, there's limitations. One limitation is that power analyses do not typically generalize very well. So if you change the methodology in how you collect the data or what statistical procedure you're using, then you'll have to redo the power analysis because power analyses make very specific assumptions about how the data are collected, what the properties of the population is, and what statistical methods you're using to make those evaluations. In some cases, a power analysis might suggest a number of subjects that is inadequate for the statistical procedure. For example, a power analysis might suggest that you need 30 subjects for a logistic regression, which we'll learn next semester, but we know that logistic regression actually requires larger sample sizes, and so you'll have to round up some amount. Okay, even though there's quite a bit of mathematics that can give you exact numbers, you have to take all of these guesses with grains of salt. Perhaps the most important limitation is that a standard power analysis gives you a best case scenario to estimate the number of subjects, and the best case scenario is based on assumptions, and if your guesses are wrong, then your power analysis could be way off. Finally, because power analyses are based on assumptions, you often want to get a range of the numbers of subjects needed rather than a precise number. So for example, if you do not know what the standard deviation of your outcome measure will be, and you have to guess at that value, you can run the power analysis and get a certain number of subjects, and then you can guess a slightly larger value, maybe a slightly smaller value, and give yourself a range of what the standard deviations are likely to be, and given that, you'll get ranges of numbers of subjects that you'll need. Okay. Other considerations of power analyses is, okay, so after all this discussion of power analyses and the necessary number of subjects, we need to stress that power is not the only consideration when determining necessary sample sizes. For example, different researchers might have different reasons for conducting a regression analysis, which we'll cover in Chapter 8 and next semester in Advanced Data Analysis 2. You might want to test whether regression coefficients are different from 0, or you might want to get a very precise estimate of the regression coefficient, so have a small confidence interval. So number 1 is about doing a hypothesis test, right? And number 2 is about doing inference about what likely beta values or regression coefficients are likely to be. And those two are different goals and may require different sample sizes. Okay, and there's a few other examples here. The last part of this chapter illustrates how you can use simulation to calculate power or calculate sample size needed or other related quantities. And so I give code with lots of comments about what is being done in that code to calculate power. And we'll see that the simulated calculation of power is very close to what was calculated before using the exact methods that are built into R. Okay, and I go through one example for head breadth data. All right, so that is the discussion of power and sample size.